To calculate the determinant of the matrix 3 of the order 3. So firstly, we write the sign as I write here for the columns. The first column we have plus, the second minus, and the third plus. Okay. So the first one, for example, if you just select I1, okay, and eliminate this one and this one. And the rest is the matrix of the second order. Okay, so here we have I1 multiplied by this matrix of the second order B2, C2, B3, C3. Okay, and for the second B1, okay, just 1 minute, select B1, okay, as coefficient, okay, and eliminate this one, and this one. The rest is the matrix of the second order. But here you must add minus, okay? This minus, okay? So B1 minus B1 multiplied by the second order matrix I2 or C2, I3, C3, okay? And the last one, is C1, the same thing. You select C1, eliminate this and eliminate this, and we have the second order matrix. Okay, here we have plus. Okay, plus C1 multiplied by the second order matrix. Okay, and there is another method which is called the alternating way to calculate the determinant of 3 by 3. Okay. This method, here we have the matrix of the 3 columns and 3 rows. Okay, this method just take the 2 rows, columns, sorry, of the first matrix and add it here, as shown in blue color. Okay, add it here and draw diagonal row like that. Just I will take this one, okay, from the top to the bottom like that. Okay, this is the first, the second, and the third. Okay, okay, this is, and another color. Okay, from the bottom to the top, okay, like that, and like that, okay, and put the sign. Here for the blue color we have minus, and for green color we have sorry, this is minus and this is sorry, okay, this is plus, and here we have minus. Okay, okay, and we calculate the determinant equal to first row is I1, B2, C3, okay, plus B1, C2, as shown here, C2, C3, plus C1, I2, C3, okay, and minus I3, B2, or C1, okay, minus B3, C2, I1, minus C3, I2, B1, okay. This is how to calculate in the matrix of the second order. But this method is only valid in the the matrices of with the order of 3. Okay, and here we have the example. Okay, here we follow, as I said, here, all right, 0, 2, then 3 minus 1, okay, and 4, 0. And we follow the same step, okay? Draw from this one, like that, sorry, like, okay? And here like that, and like that. Okay, and is equal to okay, we have 4 multiply minus 1 multiply 4, okay? We start by from the top. We have 0, 0 minus 1, 1, which is 0, plus 2 multiplied by 2 multiplied by 4, which is 16, plus 1 multiplied by 3 multiplied by 0, which is 0, then minus, just I put the, here we have just 1 minute, here we have plus, and here we have minus, okay? Minus 4 minus 1, which is minus, okay, I follow here, minus 4, okay? Plus, minus, sorry, minus 0, minus 6, okay? Here we have 16, plus 4, 20, minus 6, which is 40, okay? And we will check the next, sorry. Next page. Okay, here we have 0, 16, 0, minus 4, 0, or 6, which is 40, okay? This is how to determine the determinant of the, when we have 2 variables and 3 variables, okay? So, solving equation with 2 unknowns, okay? We start by solving equation by 2 unknowns, okay? Here we have 2 equations. We have x1 and x2 are unknown or variable, and I1, B1, A2, B2 are coefficients, okay? And Y1 and Y2 are constant, okay? The procedure for solving this equation by the method of determinants, firstly, we will write the 2 equations in the form, in the matrix form, okay, as shown here, okay, as shown here, okay. Firstly, we calculate the common determinant. The common determinant is by taking I1, B1, A2, B2, okay, and then we apply the Cramer's rule, okay. So to calculate, just okay, here the common determinant is this one, and to calculate the x1, okay, we just x1, okay, we delete I1 and I2, and I replace it by Y1 and Y2, okay, as shown here, okay. Right in here, delete I1 and I2, and I replaced by the constant Y1 and Y2 over the common determinant, okay? This is the common determinant, okay? Okay? And the same thing for the x2. Just here we delete B1 and B2, we replaced it by Y1 and Y2, okay, as shown here, okay, Y1 and Y2, okay, over the common determinant. So here we will get x1 and x2. This is for the second order equations, okay. Now for solving equations with three unknowns, the same procedure, just here we add another variable, the third one, okay. Here we have I1, I2, and I3, B1, B2, B3 are the coefficients, and Y1, Y2, Y3 constant, and X1, X2, X3 are variable. Okay, the common determinant is I1, I2, I3, B1, B2, B3, C1, C2, C3, and we calculate determinant as previous. As I said in previous slide, we can use one of the two methods, okay? And to calculate the x1, so we have here the common determinant, okay, this one, and we delete this one, we replace it by the constants, okay, to calculate x1. For x2, we delete this one and we replace it by the constant. And for the third, the x3, we delete the columns, the third columns, and we replace it by the constant. And here we can calculate x1, x2, and x3. Okay. Here when we have three or two equations to solve it. Okay. We use the Cramer's rule. Yes, here we have examples of the following three simultaneous equations by the use of determinant and Cramer's rule. Okay, check it at your home. Okay, okay.
Yes.
Yes.
Miss, there are students in the waiting room. They're
okay. Sorry. Yes. Okay. Any question? Okay, it's clear? Okay, we'll continue. Okay, try to solve this equation. Okay. Okay, we will continue. Okay, now we will start. We will pass to the source transformation. Okay. In order to solve difficult and complicated circuits, it is important to simplify the given circuit for easier analysis. Okay, one method to simplify the circuit analysis is to use a source transformation. Okay, one way to simplify a given voltage source with a series resistance can be converted into or replaced by an equivalent current source with a parallel resistance, okay, as shown here. Okay, here we have the source voltage and a resistance. The source voltage is in series with resistance, okay? And we can convert it to a current source and parallel resistance so that the current equals, normally you know that I equal to V over R, okay? R is given, okay? And the inverse is correct. When we have the current source and parallel resistance, we can convert it to the source, the voltage source and a series resistance. Also, we have here the voltage V equal to R multiplied by I, okay? This is for the independent source conversion. The same thing the same principle is applied to the dependent and sources, provided we carefully handle the dependent variables. Okay, here we have, for example, here we have a dependent voltage. Yes, and the series resistance is converted to a current with parallel resistance. Okay, just 1 minute. Yes, accept. Okay. Yes. Okay. Here we have a small example to show you how we convert how to use the source transformation. Okay. Example: use source conversion technique to find the load current IL in the circuit of this figure. All, of course, all resistance are in ohms. Okay. Our load is located here. Okay, so we try to get the current IL. Okay. IL. Okay. Look at this circuit. Okay, here we have the voltage source. Voltage is in series with 3 ohm. Okay, we can convert it to a current source parallel with 3 ohm. Okay, as shown in this figure. Sorry. Here. Just we return to here. We have 3 and 6 volts. So to convert it to the current source, we have 6 over 3, which is equal to the 2 ohm. Okay, as shown here, 2 ohm. Okay, so 2 ohm, 2 amperes. Sorry. Yes, are in parallel with 3 ohm. Okay. And 3 ohm is parallel with 6 ohm. So the equivalent is 2 ohm. Okay, 2 ohm. So here we have also, here we have 2 ampere is parallel with resistance. Okay, and resistance. Yes. So we can convert it also into voltage in series with resistance. Okay, and so the voltage is equal to 2 ampere multiplied by 2, which is equal to 4 voltage. Okay, so it is in series with 2 ohm. So we have here 2 all resistance are in series. We can add it, which is equal to 4 ohm. Okay. And here we have 4 voltage, and here the results here. Just 1 minute. The result here is 4. Okay, 4. So we have 4 resistance series with 4 series with voltage source. We can convert it also, as shown here, into the current voltage source parallel with resistance. Okay, before we have 4 over 4 volts over 4 is equal to 1 ampere. Okay. So here we get 1 ampere and 4 parallel with 4 ohm. Okay, and here, as shown in this figure, 2 sources of the current. We can add, as I mentioned in the chapter 2. We will cover. We will try to cover this chapter next week. Okay. Yes, here we have 2 sources. We can add it. 1 ampere plus 3 ampere are equal to 4 ampere. Okay, parallel with 4, and here we have 1 ohm with 3 ohm equal to 4. So here we have 2 branches. So this first and this the second. Okay. Here we have 4 ohm and here we have 4 ohm. So the current is divided in 2. Okay. So IL equal to 2 ampere. Okay. Equal to 2 ampere. IL equal to 2 ampere. It is clear? It is clear? Any question? Okay. I will continue. Okay. Do you hear me? Do you hear me? Please. I will continue. Okay. 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 This is for source of transformation. Now we will go to the first method of the analysis, which is called the mesh analysis. Mesh analysis technique uses mesh current as a variable. Mesh current as a variable. Okay, instead of the current in the element to analyze the circuit. Therefore, this method absolutely reduces the number of equations.
Please repeat the last speech.
About the
source of transformation.
Okay, I will repeat. Okay, just 1 minute. Okay. Okay, I will repeat all. Okay, just 1 minute to add your friend. Okay. I said the source transformation. Okay, in order to solve difficult and complicated circuits, when we have complicated circuit, so we try to simplify this circuit. Okay, it is important to simplify the given circuit for easier analysis. Okay, one way to simplify the circuit is to use the source transformation. The source transformation, for example, if you have a voltage source with a series resistance, can be converted into or replaced by an equivalent current source with a parallel resistance, as shown here. For example, here we have the voltage, okay, is in series with R, okay, can be converted into a current parallel with R, okay, and the current we can calculate by using V over R. Since we have voltage and R, we can calculate current. So we can convert this the voltage and series resistance into the current source and parallel resistance. And the inverse is correct. For example, if you have if you have current source parallel with resistance, we can convert it to the voltage in series with resistance. So that voltage equal to I multiplied by the resistance. Okay, this is for the independent source conversion. The same thing we can apply source transformation for the dependent sources, provided carefully handle the dependent variable. Okay, here we have the voltage. The control voltage, the current control voltage source is converted into the current control current source. Okay, with here we have the current control voltage source resistance in series with R is converted to the current controlled current source parallel with R. Okay. This is for dependent source conversion, okay? So here we have the example, okay? I will repeat the example. Here we have the circuit, okay? Yes, use the examples. Use source conversion technique to find the load current IL. This is the load. The RL is located here. Okay. Now we try to calculate a current AL. Okay. Here. Okay. Okay. Yes. As you can see in this figure, we have two sources. We have voltage source and current source. Okay. Look at the left side here. At the left side, sorry. At the left side here. Sorry. Yes, here we have. Okay, here. Sorry. Here. Okay, I draw like that. Okay. Okay, here we have three resistance in series with with the voltage source. Okay, we can convert it to current source and parallel resistance, so that the current I equal to 6/3. Normally, you know this, and equal to 2. Okay, 2 ampere. 2 ampere. So, and you can see in the first figure here we have 2 ampere parallel with 3 ohm. Okay, and here we have 2 resistance are in parallel. We calculate the equivalent. We have 1/3 plus 1/6. Okay, and all minus minus 1. Okay, and equal to 2 ohm. Okay, just 1 minute. To add your friend. Okay. Okay, here we have 2 parallel. Yes, and the equivalent is 2 ohm. And here we reach to the current source parallel with the resistance of 2 ohm. Okay, and here also we can convert it also to the voltage in series with resistance, so that V equal to 2 multiplied by 2, which equal to 4 volts. Okay, as shown here. So here this one is converted to this one. Sorry. Okay, to this one. So for voltage source, 4 volt with series with 2. And we have also 2 plus 2 in series equal to 4. Okay, and for we have 4 voltage and 4 resistance. We can also convert it to the current source as shown here. So that I equal 4/4 equal to 1 ampere. Okay, which is parallel with 4 ohm. Okay, so here, as you can see in this figure 3.5a, we have 2 current source are in parallel. We can add as I said in the chapter 2. Okay, we will cover next week. Okay, so 1 ampere plus 3 ampere equal to 4 ampere. Okay, 4 ampere is parallel to 4 ohm. Okay, and we can, here we have in this branch, I think pink, this one, this branch has 4 ohm, and 1 plus 3 is equal to 4 ohm. So here we have the current source 4 ampere. When we have two branches have equal resistance, so the current is divided into 2. So 4 IL equal to 4 over 2 equal to 2 ampere. Okay? 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 It's clear? It's clear for the source transformation. Okay? I will pass. Okay? Okay, this is the source transformation. Okay? Sorry. Now we will go to the mesh analysis, the first method to analyze the electric circuit. Okay, the mesh analysis technique uses mesh current as a variable, as I said, instead of currents in the elements to analyze the circuit. Therefore, this method absolutely reduces the number of equations to be solved. Okay, we have many equations to be solved. Mesh analysis applies the Kirchhoff's voltage law to determine the unknown current in a given circuit. And mesh analysis is also called as mesh current method or loop analysis. And mesh is the loop, the closed loop or the closed path. For example, here we have this circuit. So what is the mesh? The mesh is this one, the closed loop. Okay, this is the first mesh. Okay, this is the closed loop. Okay, and this. Okay. Okay. The steps used in solving a circuit using mesh analysis are as follows. Firstly, assign a distant current in the clockwise direction to each independent closed loop of the network. Okay, just 1 minute. Okay, so the first step is to assign a distant current in the clockwise. Okay, and we will repeat this step here. Just 1 minute. Yes. Okay, we will start here clockwise. Okay. This is the first loop. Okay. Independent. This is independent of this. Okay. Okay. This is the second one. And this is the third one. Okay. Okay. We can put here. Okay, I1, like that, okay? I2, and I3. Okay, so we return to the steps. This is the first step. The second, apply Kirchhoff's voltage law, write the loop equation for each loop in the network. Then solve the resulting simultaneous linear equation for the assumed loop currents. Okay, this is example. Okay, in this example, as I said, we have 3 loops. The first step, there are 3 meshes or loops are assigned in the clockwise direction as illustrated in this figure. Okay, here we have I1, I2, I3. Okay. Okay, now we try to solve this gas I1, I2, or I2, and I3. Okay, the second step, it is called Kirchhoff's voltage law is applied around each loop in the clockwise direction. Here, for example, for the first loop, we have 100. Here I take the inverse sign. Okay, here we have 100 minus 10 I1, okay, this one, then minus 10 I1, here, this one, I1 minus I3. Here, this is I1 and I3, okay? Minus 10 I1 minus I3, okay? And we simplify this equation to reach this to the first equation. We call it equation number 1, okay? You can check it at home, okay? The second loop, this is the second loop, okay? This is the second loop. Okay, we have 10 I2 and minus I1, this one, I2 minus plus 10 I2 minus I3, I2 minus I3, plus 50 volt, okay? Since here we have plus, here we have plus, so it's plus here, okay? Okay, so we simplify and the equation and we reach to this equation, okay? You can check it at home, okay? This is the first equation and this is the second equation. It remains the third equation for loop 3, okay? For loop 3, we go to our circuit, this one, we have 10 I3 minus I1 plus 10 I3 minus A2 plus I3, okay? I3 minus I1 plus 10 I3 minus I2 plus 10 I3 equal to 0, okay? We can check it out, okay? Now here we have 3 equations and with 3 unknowns. 3 unknowns variables are I1, I2, I3. Okay, so in the step 3, to solve the 3 linear equation, we use Cramer's rule. Okay, so the first step is to write this, the equations, the 3 equations in the matrix form as shown here. Okay, this is the coefficient. Okay, this is the variables I1, I2, I3, and the constants. Okay. So we use the Cramer's rules as a revision. Here, the common determinant, okay, the common determinant, we take all the coefficient and we calculate the determinant. As I said, here the determinant. So this is the coefficient and we eliminate this and eliminate this. And we have the matrix of or the determinant of the second order. So we have 3 multiply, you can check here, minus, just 1 minute to check here, as for example, here we have minus 120 plus 20 is 100, okay, it's correct. This is for the first, this one, okay, just 1 minute, okay. Now, as I said to you, here we have plus, minus, plus. Okay, here we have plus. Now, minus, okay, minus. Here we have the coefficient. Sorry, coefficient, this one. And we took columns, okay. So, sorry. Okay, so A here, okay, here we have minus 1 multiplied by minus, which is 1 multiply, okay, we have 2 multiply 30, 30 which is 60, minus, with minus, equal to plus 20, okay, which is 80, okay. Then now we go to the last one, this one, okay, and this one, okay. So here here we have -1 multiplied by -20 -40, okay? So 60 plus 60, okay? Now to calculate delta 1. Delta 1, as I said, for delta 1 for I1, okay? As I said, it delete the first column and replace it by the constant, as shown here. This is the constant, and calculate. The delta 2 delete the second column and replace it by the constant, as shown here, okay? And the third one, delete the third and replace it by the constant here. So I1 equal delta 1 over the common determinant, that I2 or delta 2 or over common determinant, and I3 delta 3 over delta common delta. Okay? Any question? So say if yes or no, please. It's clear? Any question? Okay. Are out? Okay. Okay, Fuller? Please. You hear me? Say yes or no.
Yes, we do.
Yes, Miss, you can continue.
Okay, thank you, thank you. Okay, now now we have in mesh methods, we have a special case, okay? A mesh analysis with current source, when we have the current source in our circuit, okay? Applying mesh analysis to circuits containing current source, dependent or independent, may appear complicated. The first case is simple, when current source exists only in one mesh, okay? The value of the mesh current equal to the current source by taking the direction of the source as illustrated in this figure. For example, in this figure, we have this current source is located in independent mesh, okay? This is independent mesh, okay? This is independent mesh, and this is independent mesh. There is no contact with the other mesh, okay? This current source is independent, is located in independent mesh, okay? So here, directly, when we try to solve this to analyze this circuit, so here we have the current source, I1 equal directly, since it's in the inverse direction, equal to -5 ampere, okay? And for the second, as the previous example here, okay, here we write the equation, and the simplified equation is here, okay? Here, I1 is known, I2 unknown, and I3 unknown. Okay, so the same as the previous, we write, we have 2 here, sorry. Here we have 2. Here we have 2 multiplied by I2 minus I1, okay, plus 3 multiply by I2 minus I3, okay, plus 8, okay, equal to 0, okay, and the simplified equation is here, okay. For loop 3, the same thing, okay. We have 3 I3 minus I2, 3 I3 plus 6 minus 8, okay. Okay, this is and try to solve this equation by using Cramer's rule, and you will get the current I1, which is It's obvious. And this is A2. Sorry, there's error here. Okay. Sorry. Here we have A2. Check at your home. Okay. Today. Okay. This is the first case, okay, when the current source is located in independent mesh, okay? But when we have the current source is located between two meshes, okay? And this is the second case. When a current source is located between two meshes, we will remove the branch having the current source, and the remaining loop is known as super mesh. Okay, this is called super mesh. So look, for example, in this example here, we have two loops. Here we have one loop and second loop. Here is the node, okay, and here the branch. So the current source is located between first mesh and second mesh, okay? When we have the current source is located between two mesh, we must delete this, remove it like that. We select current source and we remove it as shown here, okay? Exclude this element, okay? Exclude this element, okay? The current source between the two meshes, we must exclude it, okay? And here, a super mesh created by excluding the current source, okay? Here, we remove the current source, and the remaining is called the super mesh, okay? So, applying Kirchhoff voltage law to the super mesh in this figure, for example, for this figure, here we calculate directly. Okay, look, minus, just 1 minute, I will write it, equation to be clear for you. Okay, here we have minus 12 plus 9 I1, okay, here, 9 I1, directly plus 3 A2, okay, A2. Directly plus 3 A2 plus 6 I2, okay, equal to 0, okay, I'll show here, okay, and the simplified equation is here, and it's called number 1, okay. And we go to the, by applying Kirchhoff current law to a node. This is the node, okay, node, okay, in the branch where the two meshes intersect, okay, when we have two meshes, and the current source intersects the two meshes, okay, and here we have I1 minus I2 equal 1.5. Okay, here you can solve it directly by using the coefficient variable. You can multiply by 3 and delete I2, and we will get we will get I1 and I2. Okay, so when we have the current source located in the intersection between the two meshes, we must apply the super mesh method. Okay, the super mesh method. Okay, we delete it first. The first step is to delete the current source and calculate and apply, and the remaining circuit is called super mesh, and apply the Kirchhoff voltage law. Okay, and analyze the branch alone. Okay, alone by applying Kirchhoff current law. Okay. Okay. Now we pass to the second method, is the nodal analysis. The node equation method is based directly. Just a minute to check. Okay. Yes. Just a minute. Okay, based directly on Kirchhoff's current law, unlike the loop current method, which is based on Kirchhoff's voltage law. For the application of this method, every junction in the network where three or more branches meet in regard that are not. Okay, for example, in the previous, okay, in the previous this example, okay, I will return to the first one. Okay, just a minute. Yes, this one is called a node. Okay, we have the intersection of the branches. Okay, this is called a node. Okay, the steps used in solving a circuit using nodal analysis are as follows. Firstly, determine the number of nodes within the network. Okay, here we have a simple circuit. Okay, here we have this intersection of the branches. We have 4 branches are intersected in this point. Okay, and the second one is this one. Okay, and the third one is this one. Okay, the 2 nodes in the top are called node, and this one is called the reference node. Okay, this one is called the reference node. Okay, reference node. Okay, reference node. Okay, this one. Okay, the first step is determine the number of nodes within the network. Select a reference node. The reference node is the ground which is set at 0 potential, and label each remaining node with a subscriber value of voltage V1, V2, and so on. Okay, for example, in this example, here we call this one, sorry, here V1, okay, and here V2, okay, and this one, okay, and we'll use this one, is called the reference node, and here V, V equal to 0. Okay, so the first step is to select the node, okay, and select a reference node, okay, the ground which is set at 0 potential. The voltages at the other nodes are referenced the positive with respect to the reference node. Okay, just 1 minute to add your friend. Okay, here, as I said, yes, here, this is referred as the positive voltage with respect to the ground. Okay, apply Kirchhoff's current law at each node except the reference node. Assume that all unknown current leaves the node for each application of Kirchhoff's current law. Solve the resulting equation for the nodal voltages. Okay, we will see with this example. As I said, we select firstly the node. Here we have 4 branches are in this the first node, which is called V1, and the second node is V2. And here we have the reference node. Okay, the example say find V1 and V2 in the circuit in figure 6.1 using nodal analysis. All resistances are in ohms. Okay, so select a convenient reference node. Node 3, this is this one. Node 3 is the reference. Assign node voltage node 1 and node 2, and the branch count as illustrated in 6.2. Okay. Okay, here. Okay, this I1, I2, and 3. V1, V2 are node, and the reference node is 3. Okay, and assign here we have the current. Yes, the current is divided in 3. We have I2, I3, I4. Okay, and here also is divided in A6 and I5. Okay. Now, We now apply Kirchhoff's current law at the node 1 and nodes 1 and 2. Okay. Here at node 1, okay, we select this one, node 1. What we have in node 1? We have I1. Just 1 minute here. Here we have I1 equal to, here I have an error. I1 equal to I2 plus I3 plus I4, okay? Okay, here, just 1 minute, here. Okay, I will write it here, okay? Sorry. Here we have I1 equal to I2 plus I3 plus I4. Okay, I4. Okay, now we will plus I1, which is constant, equal to 8 ampere. I2 also it's constant, equal to 1, and I3 equal to I3. Equal. Sorry, here there is. Yes, I confused here. I4 equal to V1 over 3. Okay, here I4. Sorry. I4. Okay, and I3 is V1 minus V2 over 6. Okay. So here we have 8 constant minus 1. Okay, this one. 8. This 8. And minus 1 minus V1 minus V2 over 6, okay? Minus V1 over 3, okay? And then we simplify the equation to equation number 1, okay? Sorry, here there is error, okay? This one, just here, okay? And the others are correct, okay? Okay, this second node, okay, the second node, we will return to our circuit. What we have I2, I3 equal to A6 plus I5. So in the node 3, we have A2 plus A3 equal to A6 plus I5, okay? Okay. So here we have I2 plus I3 equal I5 plus I6. I5, we return to our circuit, I5 equal V2 over 15, okay? V2 over 15, okay? And I6 equal to V2 over 10, okay? V2 over 10. Okay, we have I1, which is 1 ampere plus V1 minus V2 over 6. Okay, V1 plus minus V2 over 6 minus V2 over 15 minus V2 over 10. And simplified equation is called number 2. Okay, now we have two equations, and with two variables we can solve it, and we will get V1 and V2. Okay, as shown here. Okay. Okay, we will continue nodal analysis. Okay. The nodal analysis with voltage source, the same as the mesh analysis. When we have the current source, here when we have the voltage sources. The case one, if the voltage source dependent or independent source is connected between the reference node and non-reference node. So here, for example, here, this is the node, non-reference node, okay? This is the non-reference node. And reference node. Okay. So when we have the voltage connected from the node and reference node, yes, between the reference node and non-reference node, we simply set the voltage at the node reference node equal to the voltage of the voltage source, as illustrated in this one. For example, here we have at node 1, this is V1, V2. Okay? So we have V1 minus 20 over 2. Okay? Directly, plus V1 over 20 plus V1 minus V2, sorry, this is V2, okay, over 5. Here we have 5, not okay, equal to 0. And the simplified equation is called number 1, okay. Node 2. Node 2, we have V2 minus 8ix over 2 plus V2 over 10 minus V2 V1 minus V2 over 5, okay, equal to 0. So that, don't forget here we have independent dependent source. Dependent source is a current control voltage source. So this voltage source is controlled by the current AX, and AX equal, AX is located here, okay? So that AX equal to V1 minus V2 over 5, okay? So, we write this equation and this equation, and we will get, just we replace, okay? Here, the first here, we try to simplify this one and replace AX by V1 minus V2 over 5, okay? And we have the equation number 2, okay? Now we have to simultaneously this equation 1 and 2. We can solve it by using Cramer's rules. We write it firstly by mathematics form, okay? This is the coefficient, the variable, the constant. We have the common determinant, okay, equal to 200, and V1, this is the common, and we try here for V1, we delete the first, yes, here there is a mistake also. We try to calculate it. We replace it by 200 and just a minute. Here we have 200. Sorry, I will correct it later. Okay. We delete this one and replace it by the constant V, and here we have V2. Okay. Okay. Sorry for error of writing. Okay. Yes, here, yes, we delete this one and replace it by the constant as the previous ones, okay? Sorry. Okay. Now the case number 2. If the voltage source, dependent or independent source, is located between two non-reference nodes, this is the non-reference node, okay? And this one is the reference node. This one non, and this one is the reference node, okay? Okay. Okay, yes. It's located between two non-reference nodes, as illustrated in figure below. The two non-reference nodes form a separate node. We apply both Kirchhoff's current law and Kirchhoff's voltage law to determine the node voltage. As the previous, as the mesh, super mesh, here we have, this is the non-reference node. We have V1, V2, and V3. But here, in this space, there is a voltage source is located between two non-reference nodes, okay? Which means there is a super mesh, okay? Super node, sorry. So we delete this one, okay? The super node contains the 20 volt source between nodes 2 and 3 as illustrated in figure 7 point here. This is the super node. We delete it as shown in this figure. Okay. We analyze the circuit without the voltage source, and we analyze the voltage source or the super node alone. Okay, we will go back. Apply current, Kirchhoff's current law at node V1 as shown. We have V1, and applying the Kirchhoff voltage. Yes, applying current constant at node 2 and 3. And V3 equals, just 1 minute here. Here we apply the current, Kirchhoff's current law, okay? To get relation between V2 and V, we apply current voltage law to the circuit in B, okay? And current, Kirchhoff's current law to this circuit, okay? For this circuit, we have V1 and V2 and V3. So, for the node 1, what we have in node 1? We have 10 ampere, sorry, there is not a, okay. We have 10 ampere, yes, equal to I2 plus I1, okay, as illustrated here. I2 equal, here, V1, 10 ampere, I1 plus I2, okay. I1 equal V1 over 3, okay. I1, okay, equal I1 equal, equal okay, equal to V1 over 3, okay, and I2 just here equal to V1 minus V2 all over 2, okay, over 2. Now for the node 2, we have, just 1 minute, node 2, what we have? We have I3, I2 equal, just we're doing, I2 equal I3 plus I4 plus I5. So V2 equal I2, I3 plus I4 plus I5. Okay, so that I3 equal V2 over 1, I4 V3 over 2, I5 V3 minus 10 over 5, and I2 V1 minus V2. Okay, as shown here. Okay, this is for the first. Okay, here we have V1 minus V2 over 2, as shown here. V1 minus V2 over 2. This is I2. Okay, then V2 minus 0 over 1. V2 or minus 0 over 1. 0 means the reference node. Okay, you can put it or you put directly V2 over 1. Okay, okay, then and plus V3 minus 0 over 2. V3, this one, V3 minus 0, or you can delete it, omit it, yes, over 2. Then V3 minus 10 over 5. Okay, look here. We delete the voltage source. Okay, and the circuit remains as the previous. Like this point is located in this point. Okay. Okay. Yes. So we have this equation. We simplify it, and we will get this equation. Okay. And at the same time, sorry, just 1 minute. Except, it's all except. Okay, yes. Yes, I return to here. Yes, here we have determined node 1, node 2, and at the same time node 3. Now, here we apply Kirchhoff current voltage, okay, to the super node. So we have V1, V2 minus V3 equal to 20, okay? And V2 minus V3 equal to 20. So here we have the equation with three unknowns, okay? And the same thing, we will write this equation in the matrix form, and we solve it by using the Cramer's rule. So here, this is the determinant, the common determinant. We have the coefficients, okay? And to calculate V1, which is delta 1, we delete the first column and replace it by the constant, okay? Delta 2, which refer to V2, we delete the second column and replace it with a constant, okay? And V2 equal delta 2 over common delta, and delta 3, and we delete the third column, replace it by the constant, and we have delta 3 over the common delta, okay? And we have V1, V2, and V3. Okay, this is the case when we have the supernode. The supernode means when we have the voltage source dependent or independent. Same thing, dependent or independent source located between non-reference node. I said to you that the non-reference node is this one, okay? And the bottom is the reference node, okay? So, when we have the voltage source, dependent or independent, located between the two reference nodes, so we use the supernode, we delete this source, and we analyze the remaining circuit, and we analyze by applying the Kirchhoff voltage source to the loops, okay? And we apply and we analyze the supernode alone by applying Kirchhoff's current law, okay? Okay, I think it's enough for today. Do you agree? It's enough, or I will
Yes, yes, miss, it's enough.
It's enough. Okay, just 1 minute. Please. Okay, for the next week, okay, I will continue this course, the remaining course of the chapter 3, and I will, we will do the recitation of the chapter 3, okay?
Okay. Okay.
Okay, I will tell you when exactly, okay? Which day? Do you have a question?
Miss, what about the second chapter?
Yes, we will cover all the chapters. I focus the chapter 3 and chapter 4 are which are most important, I think. Okay? Yeah. So I will start by chapter 3 and chapter 4 with the recitations. Then we will do chapter 1 and chapter 2 as a revision for you. Okay? We will cover all. Okay? Don't worry. Okay?
Okay, thank you, miss.
Okay, if you have a question, you can ask me now or by send a question by emails. Okay?
Miss, I have a question.
Yeah.
What is the difference between the dependent and the independent current and the voltage?
Yes, as we have seen this in the beginning chapters, yes, the dependent source is constant. The independent source is constant, as shown here. For example, just I will return to the slide when I, yes, here, this one. This one is the independent source, which is constant, okay? And this also, the current source, this one, and this one are called independent source, and it is constant, okay? Doesn't vary, okay? But here, which example that I found? Just 1 minute. This one, yeah, this one. Here we have this one, and just I delete the color to illustrate to you, okay? This one This one is called dependent. It depends in the current or the voltage. Okay, there are four. Okay, this is the current. This is the voltage source, but it is dependent in the current. Okay, it's dependent in the current Ix, which is equal this one Ix. Okay, Ix. This one. Look, this is dependent, which is called the current control voltage source, which means the voltage is controlled by the current. This voltage is variable with Ix, this current. Okay?
Okay, miss. Yes.
Yeah. The same thing. We have the current controlled voltage. We have voltage controlled current. Okay?
Okay, miss. Yes.
Okay. Other questions? No questions?
Oh, thanks.
What?
I said no question. Thank you.
Okay, thank you. Thank you for your attention. If you have questions, send me per email. It's no problem. Okay?
Okay.
Okay, see you next week. Okay?
Okay, miss. Thank you.
Okay.
Okay, goodbye.
Bye.
Bye.